The Experimental Breeder Reactor 1, described at the first Geneva Conference in paper number 813, is a liquid metal-cooled fast reactor built and operated by Argonne National Laboratory at the National Reactor Testing Station in Idaho. On November 29, 1955, this reactor was subjected to a power surge which reached a probable peak value of 9 megawatts. Following this incident, which resulted in some melting of the fuel elements, a temporary cave was constructed above the reactor tank to receive the highly radioactive core assembly as it was withdrawn from the reactor. With the core assembly out of the reactor tank, the hexagonal can surrounding the fuel elements was removed, along with about 1/4 of the fuel elements. The molten core alloy had extruded into the coolant channels and solidified into a mass surrounding the fuel section. The solidified material was heavily covered with oxides of NaC, sodium-potassium alloy. The pyrophoric nature of the damaged core was aggravated by the presence of entrained NaC, and after several small fires were experienced, it was decided to transfer the core to Argonne National Laboratory near Chicago, where it would be possible to continue disassembly under an inert atmosphere. In preparation for transfer, a tight-fitting stainless steel thimble was suspended around the assembly, and separation of the core assembly was accomplished by sawing through the fuel elements immediately above the upper blanket. This thimble, with the remaining 39 kilograms of uranium-235, was transferred to the laboratory site near Chicago and placed in the cave where final disassembly was to be made. When the protective atmosphere of dry nitrogen had been established, the container was opened. Disassembly began by removing upper blanket sections of the fuel elements. These broke away near the junction of the enriched fuel section and unenriched blanket. Each fuel rod, as originally made, contained an upper blanket section of natural uranium, a center fuel section of enriched uranium, and a lower blanket section of natural uranium. One of the main purposes of disassembly was to separate and recover the enriched fuel from the damaged core. Therefore, any enriched fuel still attached to the blanket section was cut away with a remotely operated hydraulic chisel. This process of separating the enriched fuel from the unenriched blanket continued throughout the disassembly operations. The separation of fuel and blanket material was verified by means of radiation measurements. The enriched portion of the rod was considerably more radioactive than the unenriched blanket. The blanket portion of each fuel element was placed in relatively large cans. The enriched fuel was collected and moved to the adjoining area of the cave, where weighing and canning operations were performed. The size of the smaller cans was selected so that each would contain 1 kilogram of enriched material. These cans were then sealed by remotely operated equipment. The radiation intensity at the surface of each was approximately 100 R per hour. The crane inside the cave was attached to one of the fuel rods, in which were embedded several thermocouple wires, and the remaining core was partially withdrawn from the cage assembly. All remaining upper blanket sections were then removed, except for those containing thermocouple wires, which were left intact to facilitate handling. It was observed that the molten fuel alloy had moved upward approximately 5 inches between the upper blanket rods. As nearly as could be determined by observation, no evidence could be seen of the unenriched blanket slugs being damaged by melting. Complete rods could occasionally be removed from the outer part of the core assembly. The jackets on these outer rods showed damage from the molten fuel alloy which had surrounded them, but the fuel slugs within the jackets were usually undamaged. The remaining core assembly was lifted by one of the special rods containing thermocouple wires. The thimble, vibrated down, loosened several large fragments of fuel material. Complete removal of the thimble exposed the remaining fuel section and lower blanket. A cut was made through the center of the fuel section. The solidified material, formed in two distinct sponge-like zones of porosity, was easily broken and exhibited no traces of ductility. These zones were well defined by a boundary consisting of white oxides of NaC. The inner zone was characterized by pores ranging up to about 1/4 inch in diameter, along with several larger cavities. The pores in the outer zone were much smaller, with a maximum size of about 1/16 of an inch. Many of the freshly opened pores in each of the two zones were observed to contain NaC. The structure of the material in both zones showed no traces of the original fuel element components, so that alloying appeared to be complete. Radioactive heating in the center area was measured, and it was observed that the core was approximately 2 degrees centigrade higher than the ambient temperature. The chromel-alumel thermocouple wires mentioned earlier were intact and unalloyed with the solidified fuel alloy in which they were embedded. The fact that the wires were undamaged indicated that the center of the fuel section had not exceeded 1400 degrees centigrade, the approximate melting point of the thermocouple alloys. Samples were taken for chemical analysis and density determination from various zones of the core throughout disassembly. Wide variations in composition were found, which indicated that the core was far from being chemically homogeneous, even within areas of like structure and density. The average analyzed composition of the melted down section was 7.9% iron, with the balance consisting mainly of enriched uranium. The densities of samples from the coarse sponge, fine sponge, and solidified material in the blanket were found to be respectively 2.5, 5.3, and 10.4 grams per cubic centimeter. The lower part of the fuel section consisted of a dense, relatively non-porous mass. This material could be fractured only with difficulty because it was tough and somewhat ductile. In this area were found at least 12 or 15 partially dissolved fuel slugs, which were jumbled together in a random manner. The fuel slugs, when separated from adjoining material, were found to have a characteristic point on one end. It was considered probable that these fuel slugs originated from the upper fuel section, and that the pointed end resulted from a difference in melting rate along the length of the slug. The dense material also contained NaC, for when freshly broken, it showed a silvery appearance and turned black within a few seconds. This was believed to be due to the formation of nitrides or suboxides of NaC. With the final disassembly of the core section, it appeared that between 40 and 50% of the fuel had entered a molten phase during the meltdown. As was the case with the upper blanket, the coolant passages in the lower blanket were filled with solidified material from the fuel section. This material had flowed downward between the blanket rods for a maximum distance of approximately 3 inches. Also, as was noted in the upper blanket, no melting damage was evident. Great care was taken in collecting the remaining particles of fuel before transferring the cans from the cave. With the complete disassembly of this core, all the enriched fuel was recovered for reprocessing. A valuable opportunity was also provided to evaluate certain safety aspects of fast reactors. For example, the fact that much of the molten enriched fuel material was expelled from the fuel section with the formation of a highly porous structure is information of extreme importance. In addition, the experience gained in the handling of this core with the unusually difficult combination of high radioactivity, pyrophoric tendency, and near criticality has been a valuable contribution to hot laboratory technology.